All right, so I did want to show you one more complicated version of separation of variables. More complicated example. Actually, let's make this an initial value problem. So we've got this differential equation, lots of x's and y's everywhere. It looks hopeless. And this initial condition, it does not have to be y of 0. You can give y of anything as an initial condition. And if you look back at this curve, y of 0 certainly will determine where it starts. But if I told you y of something else, then I could figure out which of the infinitely many solution curves I'm on. So I can tell you any point and figure out the exact solution curve. Okay, so this does look hopeless. Let's start writing it as dy by dx. If I just... Initially, I don't like fractions, right? So if I just clear fractions, multiply both sides by this thing, this is going to be hopeless. There's too much. This xy is too annoying. There's too many x's and y's everywhere. So here we actually have to be super clever. And this is annoying because the way to see if separation of variables works as a technique for your problem is to try to separate the variables, and if it works, then you're good. The problem with this is that the trying to separate the variables is very difficult and requires something very clever. So maybe you remember from high school algebra, factoring by grouping. So if you look at this, basically you have to see that the numerator and denominator both factor, but these aren't things that we normally factor. So if we take out a y out of the first two terms, that's x plus 2, and then this is minus x minus 2, so that's a minus x plus 2 in parentheses. And same thing on the bottom. If we take out a y, this is x minus 3, and this is a plus. I'm just going to write the x minus 3 in parentheses because it doesn't matter whether I do or not. And now I can factor out an x plus 2 from the top, and we're left with y minus 1, and an x minus 3 from the bottom, and we're left with y plus 1. And look, now I can separate the variables. I can multiply both sides by basically the reciprocal of this to get that onto the other side. So I'm going to do that. Y plus 1 over y minus 1 dy, and then I'm going to do my funny multiply both sides by dx trick, which don't really think of dx as a number, but you can sometimes. Funny thing in calculus. Okay, there we go. The variables are separated. Could you think of this on the first try? I don't know. Probably not. I probably couldn't either. So it's a messy problem, or can be messy problem if you don't approach it the right way, if you aren't super clever at the beginning. We may not give you something like this on an exam, but I just wanted you to see that these problems exist, and also now we'll finish this out and we'll be able to review some integration. We've done that a little bit on the homework, but we can keep doing that. So I don't know, how do we do fractions? Do we need to do partial fractions or anything crazy like that? No. The thing we want to do is make this a proper fraction, meaning we want to make the degree of the top less than the degree of the bottom. If that's not true, then it's going to be harder than necessary to integrate. So how do we do that? I'm going to take a step to do this. So if I can match the top and the bottom, this is basically like long division, but easy because it's only degree 1. Y plus 1 is the same as y minus 1 plus 2. You can simplify this back to here if you want. And the reason I'm writing it like this is so now I can separate out this fraction. I'll take a couple steps to do this. I'll do the same thing over here. I want to match the bottom, so x minus 3, and then I really wanted x plus 2, so I need a plus 5. And we should agree that this is exactly the same. Okay, now I'm going to err on the side of too many steps. So you do not have to write out all these steps, but this is separating out this fraction, right? This is like the reverse of adding fractions. I have a common denominator, I can add the numerators. Well, if I have a more complicated numerator, I can separate it out into two separate fractions. Okay, that dy, technically there should be parentheses around there. I do like good notation. I won't take points off for that. Might take points off for a dy missing. Not many. Small number of points. There we go. If you're missing all the dy's, then you might lose a lot. Okay, what's good about this? Well, y minus 1 over y minus 1 is 1. So this is the integral of 1 plus 2 over y minus 1 dy. These are now all things I know how to integrate. Integral of 1 plus 5 over x minus 3 dx. And if you get good at this, you can maybe jump from here to here in one step, or certainly fewer steps than this. I do not need you to do a lot of writing. Yeah, that would be fine. Okay, integral here, I need you to do non-zero writing, but not a lot of writing. Integral of 1 with respect to y is y. Integral of 2 over y minus 1 is log 2 log absolute value of y minus 1 equals, and then over here, integral of x with 1 with respect to x is x plus 5 natural log of absolute value of x minus 3. These absolute values do mean something now. They're not just we need to write the answer with absolute value or else we'll lose half a point or something. And then I need a plus c on one of the sides of the equation. Okay, this is annoying. I'm not in a y equals format. I can make this a little bit better. I might not always be able to write this in a y equals format. In this case, I won't be able to. How do we make it better? Let's put the natural logs together. I don't like natural logs. I can probably get this in terms of ease. And then so I subtracted 5 natural log of absolute value of x minus 3 from both sides. I'm going to subtract y from both sides, x minus y plus c. And then I can write this as 1 natural log. If I know my log properties, this is the natural log of y minus 1 squared. If it's squared, I don't technically need an absolute value. It doesn't matter. You can keep it in if you want. To the 5th power, I do need an absolute value. So a subtraction outside the log is a division inside the log. And remember, these guys in front can go into the power. That's how I did all that. Equals x minus y plus c. I'm going to go up here since I do have a little bit of space. So then this is the power I put on e to get this thing is this thing. So I'll go ahead and put that power on. E to the x minus y plus c is y minus 1 squared over absolute value of x minus 3 to the power of 5. I have y's over in the exponent here. I have y's over here. So I'm probably not going to get y equals something. I could get all the y's on one side maybe if I want, but there's no need to do that. And then also remember this is e to the x minus y times e to the c. So I could write that as k e to the x minus y equals y minus 1 squared over absolute value of x minus 3 to the 5. Note that, I should go back and write all the domain considerations. So one is that k is greater than 0 because it's e to some power. That's always positive. Did I divide by anything? Well, over here, okay, we initially had, in the problem, x could not be 3, and y could not be negative 1. Just initially, the denominator can't be 0, but I introduced, when I divided both sides by y minus 1, I introduced this y could not be 1. And actually, this y cannot be 1 means over here k can't, or the whole left-hand side can't be 0. But I don't like this absolute value. So what if I allowed that, this denominator to be negative? The numerator can never be negative because it's squared. And I've gotten rid of the numerator being 0. So what if I just allowed that as well? I can subsume that all into just allowing k to be any real number. So my domain things check out in the end. Ooh, that's really blurry. There we go. Better. Okay. I allow k to be any real number. I don't know why this is not focusing very well during this lecture. Great. So it won't always work out this nicely, but so far it has. A lot of the time it will. And do I want to say anything else about this example? Oh, the initial value I can solve for k. So substitute x comma y, basically this point, right? 4 comma 2. And I put that into here. So k, this is e to the 4 minus 2 is 2 equals, let's see, 2 minus 1 squared is 1. 4 minus 3 squared is 1. Okay, so k is 1 over e squared, or e to the negative 2. So maybe I could have left it as c and gotten c was negative 2. So, and maybe I'll write it back that way. I'll write it down here so I have some space. E to the x minus y minus 2 is y minus 1 squared over x minus 3 to the 5 is my solution in general. Is my solution to this initial value problem.